the previous section, we used the LabVIEW FPGA project template to create a LabVIEW FPGA project. By the end of this module, you'll be able to describe aspects of FPGA technology. Okay, so now let's start Lesson 3, Programming Using LabVIEW FPGA. So first we'll start off with a quick introduction to FPGA again. Then we'll talk about how do you develop the FPGA VI. We'll talk about how to use interactive front panel communication, and then we'll go to selecting an execution mode where we can figure out do we want to execute on the FPGA or do we want to simulate it. Then we'll go to compiling the FPGA VI and what happens in that process. And then lastly, we'll talk about some basic optimizations that you should use as best practices when you're programming FPGAs. So in this slide, we have the FPGA layout and components. So we talked about this a little bit before, but just as a review, on an FPGA chip, there's a couple of different things. So one is going to be your configurable logic blocks. So those are the things that are actually going to be doing the logic functions. So it's going to be doing processing, calculations, and things like that. Another thing that we have on there is the programmable interconnects. And what these do is they route different logic blocks together, and they basically do this to create the functionality that you define in software. Not only do the programmable interconnects route signals from logic blocks together, they can also route them in and out of I/O blocks to get signals into and out of an FPGA. So how does the FPGA work? Again, the programmable interconnect switches and wires route signals between various hardware resources in an FPGA, and this is how it essentially implements the logic that you've defined in software. So hardware resources on the FPGA include things like logic gates, flip-flops, block memory, multipliers, things like that. So if you want a more detailed description of how each of these FPGA components works, you can look at the link shown on this slide. So in this slide, we have an example of a visual example of how FPGA works. So let's say we're creating a VI, and then that VI is trying to calculate a value for f from inputs A, B, C, and D, where f equals A plus B times C times D. So if we look at the FPGA here, we can kind of get a high-level overview of what's going on. So let's say we've got those inputs. So you have A, B, C, and D, and you have those signals coming in through there, through an I/O block. And then those signals are routed to logic blocks on the FPGA, where it's going to actually implement the addition and the multiplication. So then these are all routed, and eventually the result of that signal is routed to another I/O block where it outputs the signal F. So you can see how on the slide the logic of whatever program you're writing is actually implemented into hardware, and there is no OS running here. So let's take a look at some of the benefits of using LabVIEW FPGA. So if you're using LabVIEW FPGA, if you know how to use LabVIEW and also learn a couple of the things specific to programming LabVIEW FPGA that we talk about in this course, you don't have to learn VHDL or Verilog. You can simply use LabVIEW to program the functionality of your FPGA. And if you have something on an FPGA, then you're going to have true parallel execution. And we'll talk about that a little more in the next slide. And then also, because the FPGA is implemented in hardware, it's going to be very reliable and very deterministic. So here we see an example of true parallel execution on an FPGA VI. So notice that we've got two separate things going on, truly in parallel. So if we look at the top one, we've got signals A, B, and C coming through, and we're doing some sort of algorithm on that, and it's going to get output to F. Then we look at the bottom, we've got X, Y, and M coming in, and those are being implemented in a totally separate algorithm, and that's going to output to Z. And if you take a look at that, when it's implemented in hardware, in this case, these two algorithms have no dependencies, so they can run totally parallel to each other. So because it's being done in hardware, this is true parallelism. These two things are really happening on the hardware at the exact same time. If you wanted to, you could add even more things, and as long as they don't have any dependencies, then all those things are happening in parallel. You can have 10 things going on in parallel. Whereas before, if you're working on a computer with an OS, then there's only a certain amount of parallelism you can get. You can only get as many parallel things going on as compared to how many CPUs you have. So one big advantage of FPGAs is you're having these things implemented in hardware, and they are executing truly parallel to each other. So here we see that the FPGA is connected to I/O resources, and it's also connected to a bus that allows the FPGA to talk to the host, or the host to talk to the FPGA as well. So if you take a look at this, if you look at the I/O resources there on the right, for every I/O resource that you have, part of the FPGA resources, so part of that FPGA hardware needs to be used to implement that communication with your I/O. And then similarly, on the bus side, part of your FPGA resources need to be used in order to implement that bus interface where the FPGA can communicate with the host. And then after that, the rest of the FPGA you can use for timing, processing, triggering, calculations, and things like that. So just know that part of that FPGA has to be used for the bus interface and also to communicate with I/O. So let's look at some of the timing benefits of FPGAs. So let's take an example of a multi-loop analog PID loop rate. So on FPGA, these loop rates can exceed 100 kilohertz, whereas if you're running this on a real-time operating system, they can only run about at 30 kilohertz. So again, on the FPGA, you're going to get faster speeds. Also, with a digital control loop rate, you can execute up to 1 megasample per second or even more, depending on the target. On FPGA, there's also this concept of a single cycle time loop. And with those, you can execute things up to 200 megahertz or more, depending on the target and the clock configuration. And we'll talk about single cycle time loops more in a later lesson. Also, as we saw before, due to parallel processing ability, adding additional computation or adding additional loops, it does not necessarily reduce the speed of the FPGA application because all these different loops and computations can be happening in parallel. Now you can describe aspects of FPGA technology. Next, we will add an FPGA VI to a LabVIEW project and view FPGA function palettes. In the previous section, we described aspects of FPGA technology. By the end of this module, you will be able to add an FPGA VI to a LabVIEW project and view FPGA function palettes. Okay, let's talk about developing the FPGA VI. So remember, there is no operating system on the FPGA. When the FPGA VI is functioning or executing on the FPGA, it's actually In the previous section, we described aspects of FPGA technology. By the end of this module, you will be able to add an FPGA VI to a LabVIEW project and view FPGA function palettes. Okay, let's talk about developing the FPGA VI. So remember, there is no operating system on the FPGA. When the FPGA VI is functioning or executing on the FPGA, it's actually being executed on hardware. When you're developing an FPGA VI, you can only download and run only one top-level VI on the FPGA at a time. Okay, so there's only going to be one top-level VI running on that FPGA. The FPGA can run independently of the host, so regardless of what the host is doing, the FPGA VI can be running on that FPGA separately and independently. The FPGA VI can also store data in memory using something called memory items and FIFOs, and we'll talk about that later in a separate lesson. When you create a FPGA VI under an FPGA target, what will happen is if you go to the functions palette, it'll populate with an FPGA palette that is specific for FPGAs. Also, when you're developing an FPGA VI, you'll usually use integer or fixed point math to perform calculations. Starting in LabVIEW 2012, single precision floating point is also supported. We'll talk about this a bit more in Lesson 7, Signal Processing. So to add a VI under an FPGA target, you'll want to go to your Project Explorer, and then you'll want to look at where the FPGA target is. So after you do that, you want to right-click the FPGA target item in your project, select New, and then select VI. So once you've created this FPGA VI, if you go to the block diagram and you try to view the functions palette, you'll notice that the functions palette will adapt to show functions that are compatible on FPGAs. So if you take a look at it, there are some palettes that are similar to LabVIEW for Windows. For example, there's still while loops. You'll still be able to do numeric and Boolean functions and things like that. But you'll also notice that there are some FPGA specific palettes as well. So you'll notice that there's an FPGA I/O palette that's specific to FPGAs, and also FPGA math and analysis and things like that. One example is the FPGA I/O palette. This is a palette on the functions palette that's specific to FPGAs, and in this palette you'll find I/O nodes, which are the nodes that you would use to communicate with I/O through your FPGA. Another palette I want to let you know about is the FPGA Math and Analysis palette. So on this palette, you'll find FPGA Math and Analysis functions that are optimized to execute on an FPGA and also use a minimal amount of resources on the FPGA. The functions will typically perform point-by-point calculations. Okay, now let's dive into LabVIEW and take a look at these palettes. Okay, so now we've got a LabVIEW project open. And notice that this LabVIEW project has a CRIO in it, and it also has an FPGA target under the CRIO. Okay, so let's say we want to create a VI to execute on this FPGA. So what you want to do is you want to select the FPGA target, right-click it, go to New, and then select VI. So let me close this real quick. And now we have a VI, and you'll notice that over here on the bottom you'll see that it is executing in the Compact Rio project, and it's also executing under the FPGA target. So let me go to the block diagram, and let me close out of this real quick. I just want to show you guys that this VI, notice that you'll see it right here, Untitled 1, and this VI actually is under the FPGA target. Okay. So now when I go to the block diagram and I go to the functions palette, so if I right click, notice that the functions palette is going to adapt to functions that are supported on the FPGA. Okay. So notice that some things in this palette are going to be similar to LabVIEW on Windows. So notice we have for loops, we have while loops, we have case structures. If you go to the numeric palette, you'll see that you have addition, subtraction, and things like that as well, and Boolean functions as well. Okay. I do want to point out that there are some other things. So let me pin this down real quick. So notice that here we have FPGA I/O. If we go to this palette, notice that we have I/O nodes, I/O constants, and these are the things that you'll use to interact with your I/O. So let's go back to our programming palette. Also, I want to bring your attention to data storage and transfer. So this is something that is specific to FPGA as well. So notice we have registers, we have memory, we also have FIFOs. Okay, so these are ways that we can store data and also transfer data on an FPGA, and we'll talk about this in a later lesson. Another one I wanted to point out real quick is also the FPGA Math and Analysis palette. So let me click into here. And notice that over here there are some algorithms that are built into LabVIEW FPGA. So for example, if you need to do scaled windows or you want to do an FFT, these are things that have already been implemented in this palette. So instead of building your own, you can just use one of these. Notice that the FFT looks a little bit different on FPGA than it looks on a Windows system. So we'll talk about these functions a little more in the signal processing lesson, but I just wanted to show you for now. If you look into here, there's other functions as well. So if I go into the control sub palette, notice that there's already a PID function that's implemented for you as well. So if you need to do PID, you can use this function. Alright, let's talk about top-level FPGA VI front panels. Okay, so as we know, with an FPGA, the hardware resources inside it are limited, right? An FPGA is going to have a finite amount of hardware resources. So one thing you need to do when you're programming for FPGA is you want to think about ways that you can try to use the minimum amount of resources that you need. So one way you can do that is you can use the minimum necessary controls and indicators for programmatic front panel communication to a host. So for every control and for every indicator that you put on your top-level FPGA front panel, there has to be some FPGA resources that are used in order to implement the logic of being able to communicate those controls and indicators back down to your host. Okay? So in light of this, you should try to minimize the amount of controls and indicators on your front panel and only use the ones that you need. Sometimes what you can do as a developer is you can add temporary controls and indicators for debugging, just so you can see what's going on inside your program. But when you're done using those temporary controls and indicators for debugging, make sure you remove them afterwards to save on your FPGA resources. Now you can add an FPGA VI to a LabVIEW project and view FPGA function palettes. Next, we will communicate between the FPGA and host PC using interactive front panel communication. In the previous section, we described how to create an FPGA VI and view the functions palette. By the end of this module, you will be able to communicate between the FPGA and host PC using interactive front panel communication. Now let's talk about interactive front panel communication. So remember, an FPGA really has no user interface, right? So the FPGA is actually just hardware, so you have functionality that's happening on that FPGA chip. Okay. So let's talk about a couple things. So to communicate data from the FPGA, you can either communicate from the FPGA through the bus back to the host PC, or you can also communicate by using your I/O lines. The front panel is displayed on your host PC. So when you're creating an FPGA VI and you run it, you're going to be able to see on the front panel some of the values that are coming from the FPGA VI, and we'll talk about this in the next slide. The block diagram that you've created for your FPGA VI, well, that defines the functionality of what you want your FPGA chip to do, right? So if you think about it, the functionality that's defined on your block diagram is actually compiled and it's executing on the FPGA chip itself. Also, there's a communication layer that shares all control and indicator values. So every control and indicator that's placed on your top-level FPGA VI, those control and indicator values are being communicated from the FPGA chip back up through the bus to your host computer. So when you're running an FPGA VI on the FPGA, you can't use any debugging tools because it's already executing on that FPGA hardware. So what you want to do for debugging is typically you want to test your FPGA VI first on the development computer. So before you even compile it and send it to the FPGA, you want to just test it targeted at the development computer and make sure all your logic and your algorithms are correct before you go through the trouble of compiling it and sending it to the FPGA. Another thing you can do is if you want to debug the FPGA VI when it's already running on the FPGA, you can add extra indicators on your front panel, and those indicators will give you values, and you can use those values to kind of debug what's happening on the FPGA. So here, let's talk about interactive front panel communication. So on this slide, you see that there is a FPGA VI, and you've got the front panel, and you also got the block diagram. So on the front panel, you'll see that there are controls and indicators, right? So you see a couple of numeric controls. You see some indicators as well, and every control and every indicator you have on there, you can communicate those values between the host computer and the FPGA target over the bus. So if you think about it, the FPGA VI front panel, it's updating with values that are coming from your FPGA. Okay, so you can think of this as your user interface almost for your FPGA VI. And if you look at the block diagram, notice that in the block diagram, that's where your functionality is being defined, right? So the functionality that you've defined on your block diagram, that is being compiled and it's being actually executed on the FPGA hardware. So if you think about it, the FPGA target is actually executing whatever you defined in your block diagram. So this concept of an interactive front panel communication, what's happening is the functionality of your block diagram is executing on your FPGA target, and then your host computer is kind of an interactive way of you being able to see the current values of your controls and indicators. You're able to see what values are being updated on there from the FPGA. Now you can communicate between the FPGA and host PC using interactive front panel communication. Next, we will execute an FPGA VI on either the FPGA target or development computer by selecting the execution mode for an FPGA target. In the previous section, we communicated between the FPGA and host PC using interactive front panel communication. By the end of this module, you will be able to execute an FPGA VI on either the FPGA target or development computer by selecting the execution mode for an FPGA target. Okay, let's talk about selecting an execution mode. So to select an execution mode, what you would do is you would right-click the FPGA target in your Project Explorer window and select Properties, and it will launch the dialog that you see on the screen. So notice if you click the debugging category, there's two ways that you can execute that FPGA VI. One way is execute the VI on the FPGA target, which is that first option there. Now when you're doing that, if you hit the run button on that VI, what it'll do is it'll compile your code and it'll actually execute that VI on the FPGA hardware. Another thing you can do is instead of executing the VI on the FPGA target, you can execute the VI on the development computer. So if you take a look at that second option, if you're executing the VI on a development computer with simulated I/O, what happens is it doesn't send that VI down to your FPGA. It keeps it on your host computer, and it basically uses simulated I/O, so you can try to verify the functionality of your VI without having to compile. And we also see a third option down there with execute VI on development computer with real I/O. So you can also have an option of executing that VI on your development computer, so you don't have to compile yet, but you can actually use real I/O from your FPGA target if this happens to be supported on your FPGA target. So another way that you can select the execution mode is you can also right-click the FPGA target in your project and then just use a shortcut menu to navigate to execute VI on, and you can select your mode directly. And we'll see that later on in the demo. So once you've selected an execution mode, you'll see in your project that your FPGA target will tell you what mode it's in. So if we look at the very top one, notice that it says FPGA target, and that's pretty much it. If it looks like that, then what's happening is you're executing your VI on the FPGA target. So in this case, if you're running that VI, it's going to get sent down to your FPGA. If we look at that second item there, you'll notice that it says FPGA target and also says development computer. This tells us that when I run this FPGA VI, what's going to happen is it's going to just execute on my dev computer, and it's not going to be sent down to my FPGA. So this is a very useful mode for you to make sure that all the algorithms and all the logic on your FPGA VI are correct before you go through the trouble of compiling it. So if you're executing your VI on your development computer with simulated I/O, you can either use random data for any FPGA I/O, or you can also use a custom VI for FPGA I/O as well. You can also, on some targets, you can also execute the VI on your development computer and use real I/O that's coming from your hardware. Okay, let's talk about testing with the development computer. So one thing I want to make sure you understand is when you're compiling an FPGA VI, that compilation can take from a few minutes to several hours. So it's something that will take a lot of time. So if you select your VI and you tell it to execute on an FPGA, it's actually going to go through this compilation process, which could take a long time. So that's why it's a good best practice, before you ever execute your VI on the FPGA and compile it, you want to go in that simulation mode. You want to go and execute it on your development computer instead first. And this way you can make sure that the logic for your VI is correct, right? So if you look at the development flow that's shown at the bottom here, notice that you'll create your FPGA VI. Once you think you're done with it, then simulate that FPGA VI on your PC to test it. And then that way you can use all your debugging tools. You can use highlight execution, you can use probes, you can use single stepping, and that way you can kind of debug your VI and make sure everything looks correct on your simulation before you decide to compile it. Okay? So keep simulating, keep modifying your FPGA VI until everything looks good in that simulation mode. And then once you're done with that and you think everything looks correct and you've done your due diligence, then only after that execute your VI on the FPGA and then go through that compilation, which may take a few minutes to several hours. And that way you'll be able to save a lot of time by going through that kind of a development flow. So at this point, it would be good for you to be able to do exercise 3.1. So if you can, go ahead and do exercise 3.1, and you'll be able to create an FPGA VI and verify the functionality of the VI using the development computer. So you'll be able to get some experience on simulating your FPGA VI before you compile it. So right now, what I'm going to do is I'm going to go ahead and demo this and demo the solution, just so you can get a high-level idea of what's going on with exercise 3.1 and also how to execute your VI on the development computer for simulation. Okay, I've opened up the solution for exercise 3.1. So let's take a look at this. So notice we have a CRIO target here, and we have the FPGA target that is under our CRIO. So we were talking about the execution mode. So one way you can take a look at the execution mode is you could right-click the FPGA target and go to Properties. This will cause this window to pop up, and then notice if you go to Debugging, you've got a couple of different modes. So Execute VI on FPGA target. Again, if you select this mode and run a VI, then it's going to compile it and send it down to the FPGA hardware. Another option is you can do Execute VI on development computer with simulated I/O. So this is a good option to use if before you compile, because you want to make sure you verify the functionality and make sure everything looks right on your VI before you decide to compile it. So notice that there's two options here. You can either use random data for your FPGA I/O. So if you happen to be using any I/O, it's just going to use random data. Or you can use a custom VI for FPGA I/O. So if you select that one, you can click on the Help button to get more information on that. So for now, I'm just going to leave it as use random data if I use any I/O. So now I'm going to click OK. Actually, I'm going to switch this back to Execute VI on FPGA target so I can show you a different way of configuring this. So the other way of configuring this, which is a little faster, is you can right-click on your FPGA target, go to Execute VI on, and notice right now it's executing on the FPGA target. Instead, I want it to be executing on my development computer with simulated I/O because I want to test it out first. So I'm going to select this, and notice now that it updates to show dev computer right here. Okay. So in this case, we've got our FPGA target, and someone has already developed a simple math VI. So because it's under the FPGA target, this VI is going to be my FPGA VI. So let me go ahead and double click it to open it. I'm just going to put that here. I'm going to show the block diagram. So right now, notice that it's going to be executing on my dev computer. Okay, so I should feel free to test it and use any debugging tools I want. Just to verify the functionality first. So let me go ahead and change this to 3 or 2. I'll change Y to 3. Then I'm going to go ahead and run this. So now that just ran on my development computer, my host PC. And notice that X plus Y is 5, X minus Y is -1, and X times Y is 6. So I've verified that it looks like my algorithm is correct, and I'm ready to go. However, let's say I didn't get my expected results and I need to debug it. Well, because I'm running this VI on my development computer, I can actually take advantage of all these debugging tools here. So I can hit highlight execution, hit run, and I can use that ability to debug my VI. I can also do single stepping, I can use breakpoints, I can use probes, and all the other debugging tools that are available to me on Windows. Okay, so this is a huge advantage of making sure you debug and test your FPGA VI on your development computer first. Okay, so now that everything's done, I can go ahead and close this. And if I verified everything looks correct, I can right-click this target, go to Execute VI on FPGA target, and once I've done that, when I open this VI and hit run, it'll actually compile it and send it to my FPGA VI. But we'll talk about that a little bit more in the next section. So note how quickly we were able to progress from development to testing, right? We had a VI that we created, simple math, and then we were able to start testing it and debugging it right away just by executing it on our development computer first. So have you ever tried troubleshooting a VI without using the debugging tools? So imagine you were trying to troubleshoot a VI and you didn't have the ability to single step, you didn't have any breakpoints, you didn't have highlight execution, you didn't have any probes either. Now, you can imagine that would be very difficult. And the point that I'm trying to make is once you're executing your VI on the FPGA hardware, when the VI is running on the FPGA, you no longer are able to use highlight execution. You're not able to use single stepping because the logic is already running on hardware. So just remember that, and by remembering that, we can remember the advantages of being able to test it on your development computer first. Okay, one is that you're going to be able to verify the functionality and make sure you're not compiling it for nothing. So first, make sure that your functionality is correct, And if it's not correct, you're going to be able to use your debugging tools to fix whatever that problem is before you decide to compile it.